Hey guys, in this video I wanted to review some practice problems on nucleophilic additions to ketones and aldehydes, and these come from Learning Target Quiz 6.1 in the spring 2024 semester in my Organic Chemistry 2 course. Okay, so these nucleophilic additions to ketones and aldehydes, the reactions we're going to see here span both irreversible additions, which are typically organometallic or hydride type reagents, and reversible additions where we're using heteroatomic nucleophiles like oxygen, nitrogen, sulfur, and that kind of thing. And the breadth of reactions here is so wide that I think it's really important to think mechanistically and step through the reactions mechanistically. This can actually help you get sort of partial credit on the questions as well, because if you write down a structure that happens to be a reactive intermediate or a plausible structure that exists in solution along the mechanistic pathway that just happens to not be the final product, this shows good mechanistic understanding, and we're going to reward that. So I'll talk through some of the things I saw in terms of the major mistakes that students made, which were most commonly plausible structures that just happen to not be the final product. So for example, in this first case, we can recognize that we have a ketone, a carbonyl group connected to two carbons, and we've got this structure here, which is a methoxy group linked to an NH2 group under acid catalysis. That H plus in brackets indicates we have acid catalysis going on. So some kind of reaction is going to occur between the ketone and this methoxyamine structure that's over the arrow here. Now, we're familiar with ketones and aldehydes as electrophiles at the carbonyl carbon, and so it's reasonable to look for a nucleophile among the reactants. And something we should notice is that this methoxyamine reagent has two potential nucleophiles. There's the oxygen and the nitrogen. And on the basis of electronegativity arguments, all other things being equal, which here this oxygen and nitrogen are about as similar as you can get, the less electronegative nitrogen atom is going to be the better nucleophile. So this is the more plausible nucleophile here. Another thing that argues for this is that the nitrogen has hydrogens that can be deprotonated later in the mechanism, while the methoxy group has no hydrogens to lose. And so this, if it does add, it does so reversibly and to a very, very small extent. So the first thing we should think about here is a nucleophilic addition of this amino nitrogen to the ketone carbonyl carbon, keeping in mind that the acid catalyst is there to protonate that carbonyl carbon. And so to draw that, we can start by adding the nitrogen at the carbonyl carbon. The carbonyl oxygen is going to get protonated, and then it's important to fill in everything else that's connected to that nitrogen. So we have an NH2 and an OMe connected to that nitrogen, and the way we've drawn this makes it clear that nitrogen has made a bond to the carbonyl carbon. So again, our nucleophile was the nitrogen, electrophile was the carbonyl carbon. We're going to see this pattern over and over again as we predict products here, and actually I'm realizing we want to erase one of those H's since that nitrogen will get deprotonated after the nucleophilic addition. So this is a neutral reactive intermediate along the reaction pathway here, and if you drew this, it's a partial credit type of situation. This is what we call a carbonyl amine. It's not the final product because water is still built in to this structure with an OH group and an H linked to adjacent atoms. So the elimination of water is still possible here, and the acid catalyst is going to mediate that, and in many cases, we actually consciously remove the water. So from here, we can, and let me pause here for a second and just say that it's important to recognize when water appears in these addition products in a situation like this, with an H linked to a heteroatom adjacent to a carbon linked to the hydroxyl group. This points to the elimination of water as a possibility. And when the amine is primary, as it is here with one R group and two H's, we can eliminate water to form a carbon-nitrogen double bond. That's what's going to happen in this case. So I'm going to erase the H and OH, and there will be a double bond between the carbon and nitrogen, and water is going to be a byproduct of the reaction here. Not essential to draw this, but since we're thinking through this mechanistically, I'm going to go ahead and add it. And then the very last thing I'm going to do is just clean up this double bond a little bit. So we have a double bond to nitrogen, and we have the OMe group also linked to that nitrogen. And this is our final product. It's an N-methoxyamine. There's a methoxy group connected to the nitrogen, but the overall process is really just an imine formation of a carbon-nitrogen formation of a carbon-nitrogen double bond where there was a carbon-oxygen double bond in the original reactant. Okay, in the second case, we again have an electrophilic ketone in which the carbonyl carbon is electrophilic, and here we have an amine with nucleophilic nitrogen, but now the nitrogen, notice, is secondary. This is a secondary amine with two R groups, methyl and propyl, and one H connected to the nitrogen. So the outcome here is going to be a little bit different. Again, we have an acid, acetic acid in this case, that's going to serve as a catalyst for nucleophilic addition and all the steps that follow. So as in the case above, we're going to get a carbonyl amine intermediate first, a reactive intermediate that is a carbonyl amine first. So the amine adds to the carbonyl carbon, the carbonyl oxygen is protonated, and what do we have left connected to the amine? Well, we have the methyl group, which I'm just going to draw here as a line. That's the Me group in the given reactant structure. And we have the propyl group, which is hanging out over here. Okay, and again, this is not the final product because this contains water built in that can be eliminated with an H on what we'll call the alpha carbon, the carbon adjacent to the original carbonyl carbon, and an OH group still linked to that former carbonyl carbon. So water can be eliminated from this structure to form a carbon-carbon double bond in this case. So we can eliminate H and OH, and we'll get a carbon-carbon double bond. Notice that the nitrogen has no hydrogens on it, so no hydrogen can be eliminated from this nitrogen, so we end up with a carbon-carbon double bond, in this case, of a secondary amine, and water was eliminated. Not essential to show this again, but let's just add plus H2O to illustrate this, and then the last thing I want to do is just clean up this double bond structure a little bit, moving that nitrogen over. We had the methyl, we had the propyl group on there as well, and this is a structure known as an enamine. Ene for the carbon-carbon double bond, and amine for the nitrogen. Makes sense? Okay, let's move to the third example. Now the third example here, the substrate does not look like a carbonyl compound. The substrate is an alkyl halide, and we're treating with magnesium. This points to the formation of a Grignard reagent where the halogen is located in the alkyl bromide. So at least as a reactive intermediate, we're going to have an MgBr here. This is an organomagnesium bromide or Grignard reagent. Now, the Grignard reagent is nucleophilic at this carbon linked to the metal. And we can see in the second step here, we're adding an aldehyde with an electrophilic carbonyl carbon. CHO indicates a CO double bond with an H linked to the hydrogen. So next, we're going to add the Grignard reagent to the aldehyde in an irreversible nucleophilic addition. So what I'm going to do is draw out the aldehyde a little more explicitly and indicate here, there's the isopropyl group, and indicate that our electrophilic carbon specifically is right here. So we're going to get a new bond formation between the nucleophilic and electrophilic carbons, like so. And let me change colors. And the oxygen on workup with water, is going to get protonated to form a neutral alcohol. Notice also that this forms a new stereocenter at the original carbonyl carbon, and so it's important here to use wedges or dashes to depict the configuration of that stereocenter. For example, we could put the H here, the former aldehyde hydrogen, on a wedge, and then add plus En to indicate that the enantiomer of this structure is also formed. So this is an example of an irreversible nucleophilic addition of a Grignard reagent to an aldehyde. And it may not be what you're used to in terms of where the reactants are laid out or lined up. This shows formation of the Grignard reagent from the substrate, quote unquote, first, followed by treatment with the electrophile and then aqueous workup. All right, finally here we have a diol reactant or reagent in combination with an acid catalyst and a substrate containing 3 carbonyl groups. Distinguishing between these carbonyl groups is important. In the bottom half of the molecule, these 2 carbonyl groups are part of carboxylic acid derivative functionality. This looks like 2 amides. right? And those amide carbonyls are actually relatively unreactive as electrophiles. Since the nitrogen is electron donating, they don't have a strong desire to react with nucleophiles. The carbonyl group at the top of the molecule is part of a ketone, and as we've seen above, that ketone carbonyl is highly electrophilic. And among the reagents used, we have this ethylene glycol molecule, or 1,2-ethane-diol molecule, with 2 nucleophilic oxygen atoms in it. And so we can think about actually both of those acting as nucleophiles, but we can treat one of them at a time to kind of step through the mechanism. So we can do what we did above with the nitrogen nucleophiles and think about just the nucleophilic addition of one of those hydroxyls to the ketone carbonyl group. So a structure derived from nucleophilic addition of one of the oxygens and proton transfers to put an H on the former carbonyl oxygen and remove an H from the nucleophilic oxygen, and now we have kind of this hanging CH2-CH2OH group. This is a hemiacetal. It's not the final product. Why is it not the final product? We still have the possibility to eliminate water from this structure. We have this hydroxyl leaving group, and we have an H connected to the other OH of the diol that could also be lost as water. And so the final product here, we're going to get rid of that OH and H and form a bond between the carbonyl carbon and the other oxygen of the diol. So to show this, I'm going to kind of wrap around that diol chain. Here's the other oxygen. This can form a bond right here, and we end up with a cyclic acetal or ketal, sort of the more old school term since we started with a ketone, and again, water as a byproduct. So the hemiacetal is good to recognize. If you got to that point and drew that, that's actually good because you're applying mechanistic reasoning. The trick here is that can react further because of the presence of OH and H in the right positions to eliminate water via an acid-catalyzed elimination mechanism. Finally, here we have a rather cryptic looking reagent with just aqueous HCl, and we have this structure that contains a carbon-nitrogen double bond with the nitrogen linked to an NMe2 group. This is known as a hydrazone. And I think the first important thing to recognize here is that aqueous HCl is going to contain water. And so essentially what we're dealing with here is hydronium ion in the form of hydronium chloride and H2O. So we're looking at a hydrolysis process here. We're looking at an acid-catalyzed nucleophilic addition of water to the hydrazone. The C-N double bond is structurally analogous to the CO double bond, which means that this carbon we can think of as a decent electrophile. Probably not as electrophilic as a, say, ketone carbonyl carbon, but enough that we can use a strong acid like HCl and water as a nucleophile to add to that carbon. So we can think about nucleophilic addition as we have been here, adding the nucleophilic O of OH at the hydrazone carbon and an H to that hydrazone nitrogen that was part of the double bond. This is a carbonylamine again, so the mechanism doesn't stop here. There's more acid around, there's more water around, and so further proton transfers can occur. And those will occur here to eliminate the, in this case, it's a hydrazine, but you can think about it as an amine, eliminate this nitrogen-containing part of the molecule, along with this H from the OH group of water that added. And so imagine we protonate this nitrogen. Now we have an NH2-NMe2 byproduct. That's one of the products of this reaction. And then we can eliminate H plus as well from this OH group, and that's going to leave us with a carbonyl group here rather. So here we have a hydrolysis that's essentially the reverse of imine formation. So compare this reaction to the first reaction we looked at, which formed a carbon-nitrogen double bond. The mechanisms of these two reactions are exactly the reverse of one another. Instead of eliminating water or kicking water off as a leaving group, we are adding water and incorporating a carbonyl group into the product. This parallelism between imine formation in the forward direction and imine hydrolysis in the reverse direction, and here water is used as a reactant and here water is a product, is important to notice in these nucleophilic additions. It allows you to see hydrolysis in the light of reactions you already know, just as the reverse of mechanisms and reactions that you've already seen. Finally, here we're asked to propose a plausible mechanism for this reaction by listing the elementary steps involved. And first, let's just take stock of what we're dealing with here. I've got methanol as a reactant. We're familiar with alcohols as nucleophilic at oxygen, so this has the potential to add to the electrophilic carbonyl carbon. I'm already thinking about steps like nucleophilic addition, since I see that an oxygen-carbon bond needs to be made here between the nucleophilic methanols, actually 2 molecules of methanol get incorporated, and that electrophilic carbonyl carbon. And there's an acid catalyst, and it's apparent that the acid catalyst is going to supply these protons that end up in water, since the carbonyl oxygen here is going to become incorporated into this water byproduct. So it's helpful here again to step through the mechanism one by one, and we're going to list the elementary steps as our final answer, but I'm going to draw out some reactive intermediates to help us visualize this. The goal of listing the steps is for you to verbalize and sort of talk it out and visualize the mechanism without getting too in the weeds on the intermediate structures and the curved arrows and the exact electronic motions involved. We want to try to think about this at a bit of a higher level. Okay, so initially we've got an acid catalyst, and we're familiar with protonating the carbonyl carbon. This is the first thing that's going to occur, and it's going to make that carbonyl, protonating the carbonyl oxygen, sorry. That's going to make the carbonyl carbon much more electrophilic, and at this point, methanol can come in and add to that carbonyl carbon. So this is just a bit more specific depiction of the mechanism that we've talked about already to this point in related problems where we've added a heteroatomic nucleophile to the carbonyl carbon. And so this reactive intermediate here, kind of running out of space to depict that methanol that's added in, but this reactive intermediate looks a lot like a hemiacetal, and in fact it is a hemiacetal just with an extra proton on there. And so if we lose that proton, we get to a neutral hemiacetal intermediate. Losing a proton from the methoxy oxygen is going to get us to a neutral hemiacetal. At this point, we still have that acid around, right? And so the OH group can get protonated, and this is, we're now setting up the possibility of the elimination of water here, right? If I protonate here, I now have the possibility to eliminate water, and this is going to form a stabilized carbocation. And I keep saying eliminate, but you can think about it as just loss of a leaving group, actually, right? We can kick off water to form an oxygen-stabilized carbocation here. So take a minute if you need to and pause the video and make sure you can see and draw curved arrows for the conversion of this cation to this cation. At this point, water can come in. At this point, a methanol molecule can come in, add to the carbonyl carbon, and that's going to get us to almost the final product. So here we have more methanol around. We're using solvent quantities of methanol in reactions like this, and so now we have something that looks kind of similar to the hemiacetal, except now there are 2 methoxy groups linked to the former carbonyl carbon instead of an OH and an OMe group. And notice the only difference between this and the final product is loss of a proton. And so the final step here is just going to be a proton transfer to lose that proton. Okay, so now let's go back and label these steps now that we've laid out all the reactive intermediates that are involved. In the first step, we have a proton transfer to go from the neutral ketone to a protonated carbonyl, and then methanol comes in here in this second step, and we have a nucleophilic addition as we've drawn it here. Of course, if you like to work from the carbocation resonance form of this structure right here, that's completely fine, and we would label that A sub N, nucleophilic attack, as opposed to nucleophilic addition. That is pure semantics and pure preference. Both of those are completely fine. And I do just want to note that methanol is going to come in here. Next up, we have another proton transfer to get the neutral hemiacetal intermediate, and we've done the familiar pattern of put the proton on, do the business, here it's nucleophilic addition, and then take the proton off to get a reactive intermediate. We're going to do that dance again. We're going to put a proton back on. This time, the oxygen that leads to the formation of a water leaving group, And kicking off that leaving group, the way I've depicted it here, looks like a beta elimination. Again, if you like to think about carbocation structures instead of these structures with oxygen with formal positive charge, we would just call this D sub N, or loss of a leaving group. And we're going to, at this point, add water in. So methanol, the second molecule of methanol, comes in at this point. Add methanol, not water. And then finally, we're going to lose a proton. So notice here again, we've got a proton transfer. We've got a couple of business steps: elimination followed by nucleophilic addition, and a final proton transfer to generate the neutral product. So this is the mechanism of acetal formation. And it's important to see it as a nucleophilic addition catalyzed by acid. Initially, that's the first 3 steps, and then an acid catalyzed substitution in the last 4 steps. We can think about this almost as SN1, but catalyzed by acid. We set up a good leaving group, we kick that leaving group off, the nucleophile comes in, and then we lose a proton to get to the neutral product.